Come on, record. Go on. I'm hoping you'll start recording. Yep. Okay. Good afternoon. And agenda today. I'm going to start with an example on unsymmetrical loading first, like what we have learned from last week's lecture. And then we are going to continue on an example for thin-wall analysis, which I did not complete during tutorial today. Okay, so I'm going to do that after I finish this example. Okay. By the way, homework 08 has been posted. Okay, it's on Avenue to Learn, so watch for it. Okay, it's already been posted. So yesterday, right, we finished off. Okay, just to recap, we finished off regarding unsymmetrical shear. Okay, so what we are trying to do now is once we have allocate unsymmetrical shear, right, we have to induce a shear center. And the purpose of this shear center is to ensure that what? We eliminate the twisting. Okay, we totally got rid of the twisting. Why we want to eliminate the twisting is because we want to apply the formula which is equal to shear stress is equal to VQ over IT. Okay, so in order to apply this formula, okay, we cannot have any twisting phenomena. Okay, so the shear center over here will offset the V. Okay, offset V means is the shear force. Once this or why the offset is necessary, without the offset, what we get is a twist over here, right? So we will have a twist without the offset. Okay. Once we have the offset, okay, the V multiplied by E, okay, and together with F multiplied by a certain distance of H over 2, for example, okay, we tend to generate a what? A counter what? A counter twist. Okay, so this is a counter. Right, so by applying Newton's third law, action equal to reaction, we got rid of the twist, and then we can apply this formula, which is shear stress is equal to VQ over IT. Okay, so that's where we finish off. Okay, it's very abstract at this stage, but it's going to be real easy. The main thing about this topic over here, again, is how you construct your shear flow. Okay, so today's tutorial, everyone is happy, hunky-dory regarding the shear flow. I hope so, okay? Now, before I go on, I like to firstly declare this, okay? I like to declare that F denotes, okay? So whenever from here on, you see F, okay? So F, which is this F over here, and you also see the V over here. This V, they are all the same, okay? And then you see F prime. So F, right? F, it denotes the shear flow in the horizontal, sorry, not the shear force, the shear flow, the shear force in the horizontal direction, sorry, and V denotes, right, it denotes the shear force right in the vertical direction. I want to get this right from you guys. Okay. Okay. So we get this clear. So we're going to look at the first example, example number 1. Okay, so some of you are copying. I'll make sure you can see. So we're going to go into example number 1. Yeah, and I picked an example that there's a lot of components in there, okay, which you will learn. Okay, pick an example. So the example I pick, again, this question is available on Avenue to Learn. Okay, I've attached this figure. Okay, so let's look at this now. So this is extruded beam, okay, has a cross section as shown. the location of the shear center is at O. Okay, so sorry, they want us to find, okay, determine the location of the shear center. Okay, so we have to find what is E. Okay, and the distribution of the shear stresses caused by the vertical force V shown applied at point O. Okay, so we have to find stresses at point A, point B, point D, point E, point F, and point G. Okay, so I'm gonna write down the solution procedure. Okay, where we're going to write down. So the first of all, this is the solution procedure. Okay, so we're going to look at the solution procedure. All right, so the solution procedure. So first of all, we have to find, okay, first, as usual, first we have to find. Why do I need to write first? It's the first bulletin, Eugene. Come on, we have to find the first moment of area. Okay, we have to find the first moment of area, which is Q is equal to a y bar, right? About each section. Okay, so this is what we're going to do first. Then after that, okay, we know we're going to apply, okay, we're going to apply that shear stress is equal to VQ over IT. Let me see this. Does this we apply? Yeah, we're going to apply shear stress is equal to VQ over IT. Okay, so we know regardless of which section that we are going to look at, okay, regardless of which section, we're going to apply rule number that one that we have known, and the note is V and I are constant, right? That's why this is so important. If you don't assume V and I are very constant, you will say, Eugene, AB, what is the shear force? BD, what is the shear force, right? So we're going to assume that V and I are all constant in this function. Then after that, we are going to find the forces. Okay, so to find the forces, right? So we're going to find F. We're going to find F. F over here denotes the horizontal force. Okay, it denotes the horizontal force. So the horizontal force, right? So once you get the horizontal force, okay, how you get it? You integrate the shear stress multiplied by dA. Okay, now the integration is Mickey Mouse stuff. Okay, nothing like what you learn in 2ZZ03 or 2ZZ010. Okay, nothing like that. Okay, then after that, following from here, we're going to take. Okay, so we're going to take moment about point C, and you ask me where is point C. So this point over here, we're going to call it our point C. Okay, so then we're going to find the position of the shear center. Okay, find the position of the shear center, and lastly, we're going to calculate the distribution of the shearing stress. Okay. Now, can someone tell me if this were to be thick wall? Okay, if this were to be a thick wall, is it necessary, okay, to do unsymmetrical loading condition if this were to be a thick wall? Question, come on. Anyone?
No.
Why? You are absolutely right, Nathan. You're absolutely right. If this were a thick wall, you don't need to do this procedure at all. And the answer is no. Any idea why? Anyone?
Is it because there's no horizontal force?
No. There is horizontal force. Okay. Why? Anyone?
I don't know, because the walls are thicker, so they're not going to bend as much.
You are almost there, Nathan. Okay. So if it's thick wall, do you have twisting? Anyone? So assuming that the structure is rigid enough, okay, for thick wall, based on the force that we apply, there will be zero what? Twisting. So you don't need to consider answer. So this unsymmetrical shear is basically when you have a what? A twist. Okay. That's why it's very specific that for this sort of analysis that we're looking at, it is always classified under what? Always. Thin wall. Always. Okay. And thin wall is inheritance that we have the what? We have the twist. Okay. Remember that. Okay. Remember, it might be a term test question. Right. So let's start from here. So we are going to consider, okay, we're going to consider this structure, and the first thing we're going to find, like anything else, we need to find what is our second moment of area. Okay, so we're going to find our second moment of area. So I'm going to start on a new page. Okay, so let me copy this first. Come on, let me copy this, you cheeky sort. Copy. Come over here. Okay. Right. Okay. So we're going to calculate the second moment of area. So I'm going to draw my transformation. Right. This is our y. Okay. And this is our z. Okay. So we're going to calculate. So we are going to divide this. Okay. I'm going to divide this here. Okay. And I'm going to divide this here. So that's how I divide it. Okay. So I draw a solid line. This is how I divide it. And I'm going to call this my 1. Right. And then this is my 2. And then finally, this will be my section number 3. Okay. So we are aware that over here, right? We are aware that this over here, this is our centroid based on observation. Okay. So this is our centroid. Okay. So IZZ is equal to IZZ1 plus by IZZ2 plus by IZZ3. Okay. Right. So now we're going to verify what's our width. So what we want to find is ZZ. So this is ZZ. Okay. So by now you guys will be very familiar. If we're going to find ZZ, this will be our width. Okay. So this direction will be our depth. The perpendicular geometry will always be the depth. Again, the axis of interest is IZZ, so ZZ axis of interest to find the second moment of area. Okay, so IZZ1 is equal to, so I'm going to write this down. Okay, so so note, before we go on, note that IZZ1, okay, IZZ1 will be equal to IZZ2. Okay, IZZ1 will be equal to IZZ2, right? IZZ2. So in this context, I will write down my IZZ is equal to twice, okay? And then the width is 4, the thickness, I'm just going to call it T to power 3 divided by